If you watched the previous video in this unit, you'd know that an exponent of 1 over n is the equivalent of finding the nth root of that number. But then I asked you guys this question: what if we were dealing with numerators other than 1? Like in the example 9 to the power of 3 halves. What should we do here? Good morning class and welcome to Sneezy Teachers, and today we're going to learn what to do with a fractional exponent that has a numerator of something other than 1. Phew, that was a bit of a mouthful. To answer this, we're going to use the same mental models we did last time. If you think of 9 to the power of 3 halves as 9 to the power of a half times 9 to the power of a half times 9 to the power of a half, you would get the square root of 9 multiplied by itself 3 times, because 9 to the power of a half is equal to the square root of 9. And we know that anything multiplied by itself 3 times is being cubed, so we could write this as the square root of 9 cubed. If you use the index law for powers, you can work it out that way as well. 9 to the power of 3 halves is equal to 9 to the power of a half cubed, because multiplying the exponent inside the bracket with the one outside the bracket gives us our original 9 to the power of 3 halves. So what's the answer? Well, given that 9 to the power of a half is simply the square root of 9, which is 3, 9 to the power of 3 halves would be equal to 3 cubed. 3 cubed is 27. So there's our answer. 9 to the power of 3 halves is equal to 27. If you understand the basic rule for fractional exponents, this is actually a lot simpler than it looks. The denominator of the fraction is the root, and the numerator, well, that can just stay where it is and function as an integer exponent on its own. If you prefer the expandotron model instead, remember that a base of 9 means that our trusty number 1 will multiply at a rate of 9 per minute, and therefore, every 30 seconds it will multiply by the square root of 9, or 3. So if we stick it in the machine for 3 intervals of 30 seconds each, we'll get 1 times 3 times 3 times 3 equals 27, which is the exact same answer we found before. So the rule is a to the power of m over n is equal to the nth root of a raised to the nth power. One thing to note, it doesn't matter which order you write this in. You can calculate the root first or the power first. You'll get the same answer. I calculated the square root of 9 first before I cubed it, but we can work it out the other way around as well by calculating the square root of 9 cubed. 9 cubed is 729, and the square root of 729 is 27. It's the exact same answer. The only reason I chose to perform the root function first earlier is because it makes the numbers smaller and easier to deal with. Let's try another example. How about 64 to the power of 2/3? Well, following the rule, we would get the cube root of 64 squared. Now remember, we could square the number 64 first and then calculate the cube root, but like I said, I'd like to deal with smaller numbers if possible, so I'm going to cube root it first before I square it. The cube root of 64 is 4, and 4 squared is 16. So 64 to the power of 2/3 is 16. And again, if you like the expandotron, this is like turning the dial all the way to 64, but only putting the number in for 40 seconds. How big will it get inside the expandotron? Well, if every minute it's multiplying by 64, then if we break up that minute into 3 intervals of 20 seconds each, then every 20 seconds we should be multiplying by 4. After 40 seconds, we'll have 1 times 4 times 4 equals 16. 64 to the power of 2/3 is 16. Sometimes we'll be dealing with numbers too large to calculate mentally, but if that's the case, we can just input what we know into a calculator. For example, if we had the 10th root of 4 raised to the power of 7, we could convert this into a fractional exponent. So we would have 4 to the power of 7 over 10. Putting this into the calculator and rounding to 2 significant figures, we'll get 2.64. Have you ever seen a question like this? If so, don't panic. This is not as hard as it looks either. There are several ways to work this out. The square root of 16 is 4, and the square root of 4 is 2, so the square root of the square root of 16 is simply 2. What if we wanted to rewrite this in index form? Well, then remember that the square root of 16 is the same as 16 to the power of a half. So by rearranging slightly, we'd get 16 to the power of a half to the power of a half. Our index law for powers tells us that we can multiply these exponents. So we would have 16 to the power of a half times a half equals a quarter. Or in other words, we're looking for the fourth root of 16, which is 2, just like we found earlier. And it makes sense too once you draw out the factor trees. 4 is the square root of 16, so the square root of 4 will be the fourth root of 16. In my next two videos, we're going to be talking about radical properties in a little more depth, and then I'm going to go through some worked examples with you guys, including ones where the base or the exponent is an unknown variable. Let me know down below what you thought of this video. If you have any questions or comments, I always appreciate your feedback. If you like this video, please give it a big thumbs up, and I'll see you next time at Sneezy Teachers. Bye!